Okay, so without further ado, Mladen Bestvina from the University of Utah talk about Teichmüller theory in outer space.
Thank you. Can you hear me? Okay. So I'd like to thank the organizers. This is my very first Ahlfors-Bers. And I'm really honored to be here. So my plan is to talk about outer space. So I think many of you know that I've been thinking about this for a few years now. And I should say that the theory is largely motivated by Teichmüller theory. That's what, we know what we're supposed to be proving by looking at Teichmüller theory. And in particular, works of, say, Bers and Thurston in the old days, and then more recently, Mazur and Minsky, and then even more recently, Raffi. However, this being in the Halloween season, you should expect to see a dark and shadowy world with monsters lurking in the background. So in many ways, the out-FN world is one way to put it is to say less nice, more challenging, but it's also, I think, more interesting. I think from a point of view of somebody working in out-FN, mapping class groups and Teichmüller space look fairly tame. Somehow, basically, everything that can go wrong probably does in the out-FN world. Okay, so I'm going to try to explain part of this world to someone who is maybe familiar or somewhat familiar with Teichmüller theory. Okay, so that's the plan. Okay, so I'll start by defining what outer space is. So the first section is outer space. And I'm going to be developing kind of a dictionary as I go along. And the dictionary says this is Teichmüller space. This was defined in the 80s by Calder and Veltman.
Can you move the microphone so it gets a little more volume?
You mean closer to my mouth, I guess? Okay, how's that? Is that better? All right, is that better? No? No? Let's see, I guess if I talk like this, then it's any suggestions? Volume, can I?
No idea.
This is an out-FN phenomenon here.
Yeah, Teichmüller theory, this never happened. How about now?
How about now? Okay. All right. I can also just try to yell. Forget the microphone. Okay. Okay. So this was defined by Calder and Veltman in the 80s, and it goes like this. It's so CVN. This is going to be the space of pairs, if you want, consisting of a metric graph. So gamma is a metric graph. And by graph, I always mean the finite, no valence 1 vertices. Volume 1. Okay, so the sum of the lengths of the edge. So you're assigning a number, a length to every edge, and the sum is supposed to be 1. And G here is so-called marking. It's a homotopy equivalence from some fixed graph, like the rows of rank n. So Rn is just a wedge of n circles, like this, to gamma. So and that's a homotopy equivalence. So this is just supposed to tell you how to identify the fundamental group of gamma with the free group. This Rn is just once and for all, it's a fixed graph. So you can see the resemblance between this definition and definition of Teichmüller space, where you consider hyperbolic structures on surfaces instead of metric structures on graphs. And there's an equivalence here if you have two of these. So here's G and here's G prime. Going to gamma and gamma prime. So these two things will define the same point in outer space if there is an isometry. In other words, a homeomorphism which preserves the length of edges, so that this diagram commutes up to homotopy. Okay, so that's the equivalence. there's a picture that one can draw in rank 2. And that's as far as we can go. Rank 3 is already too high dimensional. So this thing has dimension 3n minus 4. Is that right? 3n minus 6. Yeah, 3n minus 4. OK, so in rank 2, you start to draw the picture by you give yourself a little circle just to guide your picture, but the circle is not part of the space. And then you tessellate it by ideal triangles, just like the modular group tessellation of the hyperbolic plane. And these triangles represent families of graphs that have the same underlying graph, but the metric varies. So, for example, this big triangle over here will correspond to some fixed graph like this, where you have lengths of edges A, B, and C, and they have to add up to 1. So that describes a 2-simplex. But notice that the vertices of the simplex are not in the space, because vertices will correspond to the situation where 2 of these numbers are 0. And that's not allowed, because you're then getting a graph that's not homotopy equivalent to the rows anymore. Now, when you approach the face of one of these triangles, then one of these edges will shrink, and you'll just end up with a different looking graph, so that edge is collapsed. Now you can proceed to the next triangle, and you'll get the same looking graph as before, but it will have a different marking. You should think of taking one of these circles and then flipping it over, and then uncollapsing the middle edge, for example. Okay, so that in the first approximation, this is outer space in rank 2. There's sort of an annoying addition to this, because there's one more shape of graphs that you have to worry about, namely this sort of thing. And so it turns out that you have to add triangles like this on top of this picture. You have to attach along the base of the triangle to every edge in this picture. Okay? So there are these sort of flaps hanging off. And these sides are not in the picture, because they correspond to collapsing one of the circles to a point. Okay, so in general, CVN is the outer space is a complex. It's not a simplicial complex. It's a complex of simplices with missing faces. So simplices with missing faces. Okay, so here the zero-dimensional faces are missing, and then in this picture, even the one-dimensional faces are missing. It is contractible. That's somehow the main topological fact about outer space due to Cullen-Bultmann. In general, it is not a manifold. I mean, here you can kind of cheat and say, well, let's not attach these. Just ignore graphs with separating edges, and that's a legitimate thing to do, and it helps you in rank 2. But in higher ranks, it doesn't help you. Even if you delete those simplices, the space will still not be a manifold. So it's not a manifold. Okay, so this is one of the monsters that's lurking in the background here. It's not a manifold. But on the other hand, out Fn, which the dictionary says is the mapping class group. It acts by change of marking. Just like in the case of a mapping class group. If I have an automorphism of a free group, I can view it as a homotopy equivalence of the rows, and then I can just compose the marking. Okay. You can talk about the thick part, just like in Teichmüller space. So this just means that it's the subset where there are no loops shorter than some fixed number epsilon, right? So all loops in gamma have length. So the length of a loop is you just add up the lengths of edges that it crosses. Have length greater than to epsilon. So this is epsilon thick part. And the action of out Fn is proper on outer space, and it's co-compact on the thick part. So this is co-compact. You can, in fact, even go all the way down to the spine. There's a natural spine which is somehow dual to the missing faces. So, for example, for the triangle with missing vertices, the dual spine would look like this. You take the barycentric subdivision, and you only keep the simplices that are disjoint from the missing faces. And you do this for every simplex in your in outer space, and that's going to give you a deformation retract, an equivariant deformation retract, which actually has the right dimension. It has the dimension of the spine is the virtual cohomological dimension of the fin. Okay. Now let's talk about the boundary of CVN. So this was also introduced in the 80s by Collar and Shailen, Collar and Morgan. And the way this works, so this is, the dictionary says this is PML. So this is supposed to be analogous to the Thurston boundary of Teichmüller space. So you can think of alternatively, you can think of CVN, this outer space, by taking universal covers. You can think of a point as being an action of the free group on a tree. So this is really the same as free simplicial FN trees. And then instead of normalizing by volume, you can just say mod out by homothety, for example. Okay, and then this sits inside a larger space where you don't insist on the trees being free and simplicial. You just omit those. You allow non-free and you allow non-simplicial trees as well. So this is inside the space of just FN trees.
What's an FN tree?
What's that?
What's an FN tree?
A tree with an FN action on it. FN is acting isometrically on a simplicial tree. Just take the universal cover of one of these objects. Like, for example, the rows, take the universal cover, and that gives us a tree. Okay, so FN trees divided by homothety. And you can take the closure of this object of CVN inside here, and that's the compactification. Collar and Morgan proved that this is in fact compact. So this is compact. Okay. What's not equal? No, this is, oh, sorry, this is not equal. This is a subset, yes. It's not equal. In fact, yeah, so what's an example of something that shows up here but not here? Well, so for example, I can take, well, just to start, so I can draw the picture easier. If you take a surface and you take one of these laminations, let's say you take one of these more generic laminations where complementary components are ideal polygons. So in the universal cover, you see, let's say they're triangles. You see a picture like this. So on. And so now you can form the dual object. The dual object of this picture upstairs is a tree where I have maybe I have I call it the vertex, but it's really a branch point. The vertices or branch points are going to be dense typically in a tree that's in the closure here. So I would take a point. There would be a point in the dual object for each one of these complementary regions. And I can measure the distance between two such points by using the transverse measure. With a transverse measure, I can measure the distance between points. And that gives me a tree, which is called an R tree. So there is a dual R tree. So an example is so T could be a tree dual to a measured lamination on a surface. Now, if the surface is closed, it has the wrong fundamental group. So I really want a surface with boundary or a surface with punctures, and that's going to give me an FN tree. Okay, now more generally, so now we're getting into the monster part of this section. So if all trees in here look like that, then life would be good. But they don't. So more generally, there are trees there are trees T in the boundary of CVN, that are dual. They're not dual to a lamination on the surface. They're dual to a measured lamination on a, say, 2 complex, which is not a surface. And just to give you a little picture to think about, one way to construct laminations on surfaces is to take an interval exchange map. So you take some interval and you cover it by, you partition it into subintervals, and then you rearrange the subintervals in some other way. And then let's say this is A, B, C, and then this is I don't know, B, C, A, for example. Well, that's not very interesting. Well, it doesn't really matter. And then you can glue bands to this. So you take a band that goes off this way, and then it's glued to A here. And you do this with all pairs, B to B, C to C. That's going to give you a surface with a, well, in this case it's a foliation, but you can also think of it as a lamination. Now, this more general object, when you have a 2 complex, you can think of that as having these collections of intervals, pairs of intervals, that don't form partitions of the interval. They look like something like this. Here's your interval, and then there's maybe, there's A, there's a B like this, and there's I don't know, there's a C. So they don't form a partition. In some places they overlap. In some places they don't cover. On average they cover. And then there are also these, so maybe there's a B, and there's a C. I just have to be careful not to draw a picture that's too silly. But it's something like this. So you have places that are covered only once, and then you have places that are covered more than twice. But on average, things are covered twice. And then you do the same thing. You glue these bands, and you get some kind of a 2 complex with a foliation on it, measured foliation. And the dual object is, well, depending on how you choose these lengths and so on, but there are a lot of points on the boundary of outer space that are dual to a foliation like that. Now, even more generally, so this is all stuff in the 80s. The trees like this can be understood using something called the Rips machine. And this thing is, the dictionary says this is like the Rousey Beach induction. But it's a little bit more general because you have to handle these more general patterns of pairs of intervals. But even that doesn't describe all trees in the boundary. So this was all understood in maybe early 90s, but much more recently, by the work of Gulbois, Hillian, Lustig, and Reynolds. So even more generally, T in the boundary of CVN is typically dual to a measured. So this will have to be put in quotes. Lamination on a space which is not even a 2 complex. It's a space built of so it's sort of a complex. It's a complex built out of compact trees. So a dendrite. So take a dendrite with maybe infinitely many branch points. A compact metric tree out of dendrites cross I. So you see one of these old-fashioned complexes was built out of interval cross I. So those are called bands. These are band complexes. But now we replace intervals here by compact trees like this. There's infinitely many branch points. Okay, so these are, and then you build a space out of those things cross I. You build sort of a band complex out of that. And then the claim is that the typical tree in the boundary is described by an object like that. And there's a generalized Rips machine that handles things like this. Okay.
Sorry, does typical mean, have you described everything now?
That's where I'm stopping with this section. This really is typical in the sense of G delta dense, for example.
But no, my question is every boundary point one of these now that
Yes,
you put on the board?
yes, yes. We now, I mean, in principle, we now understand every single point. Before, in the old days, we had to approximate. So these were called geometric trees, and then these guys are non-geometric, and they can be approximated by geometric. But now we understand what they look like. Okay, number 3 is currents. Okay, so this is another sort of monster. So you want to have intersection number. Like if you have 2 measured laminations on the surface, then there's a well-defined intersection number. Well, if you have 2 trees, well, there is a notion of intersection number, but it doesn't behave well. It turns out that the dual space is really the space of currents. So in other words, instead of just having one space, PML, with a well-defined intersection number, we actually have 2 spaces, and the pairing is defined between them. Okay, so it's not a self-dual object, if you want. There are 2 spaces. Okay, so this is in the dictionary. This is also PML, but this is sort of the other PML. Okay, and in the first approximation, this is the completion of the space of conjugacy classes. See, if you have a simple closed curve on the surface, then you can either view it as such, you can just think of it as a simple closed curve on the surface, or you can take the universal cover and take the dual object and think of it as an action of the surface group on the tree. And in the PML world, both of these points of view lead to pretty much the same space. But in out FN, they don't. They give you 2 different spaces. Okay, so more precisely, a current is a, well, technically radon measure you take the boundary of the free group, which is Cantor set, and you take pairs of points and you delete the diagonals. You think of a point in here as being a line, right, with endpoints at infinity, and you divide by the flip, Z2. Okay, so these are unoriented lines. So radon measure, you should just think of that as meaning that compact sets have finite measure, and the measure on the compact sets determines. So you should just think of this as being really defined on compact sets. And to make it more concrete, how do you so if G is a conjugacy class, how do you assign to it a measure like this? And then all the other measures are going to be sort of the closure of that. So here I'm going to draw the free group as a circle. It's easier to draw a circle than to draw a Cantor set. But this is supposed to be the boundary of Fn. And now if I have a compact, suppose I have a compact set in this space. So that really means I have maybe 2 disjoint compact sets. Here's A, here's B or something. I take 2 disjoint compact sets in the boundary, and they determine a single compact set in here. And I look at the lifts of G. So the lifts of G, there will be infinitely many lifts of G. Some of them will go from A to B. So I count how many. And that's the measure. So that's the counting measure. So the number of lifts, okay, that go from A to B. And then take the closure in the space of measures, and that's the space of currents. And there's a pairing. So first of all, the space of all currents. Space of currents. It's a convex cone, infinite dimensional, except in dimension 2. But I mean in rank 2. In rank 2, it's not infinite dimensional. Well, Now, the way I defined it is. In reality, there is a slightly smaller space that people work with, and that one is finite dimensional in rank 2. But in higher rank, it's also infinite dimensional. Okay, so convex infinite dimensional cone. Okay, so it's a cone like this. You can scale measures. You can take positive linear combinations, and the projectivization is compact. Okay, so it very much looks like PML, except that it's infinite dimensional. But the good news is that there is a pairing. So you can so there is a pairing between currents and I didn't use this word before, but very small trees. So the trees in here are called very small. The ones that are in CVN bar. These are called very small trees. And there is a characterization of these trees, which I won't get into. But anyway, so very small trees. So here I'm not projectivizing. I'm taking unprojectivized currents and unprojectivized trees, and there is a map into 0 infinity, which is continuous, and it extends. So this is a theorem of Kapovich and Lustig. And it extends the obvious pairing on. So if I take mu g here, if I take one of these currents that I constructed over there, and I take some t in CVN, then there's kind of only one thing this can be. This is the translation length of g in t. Or if you want, you realize g as a loop in the quotient in this graph, and you look at the length. So this is translation length. Translation length of g in t. Okay, and these things are dense in these spaces, so this rule uniquely determines this pairing. Yes. Oh, yes, I do. I forgot that. Thank you. Fn invariant. Fn invariant Redon measure. Thank you.
How would the factorization of a dimensional cone be compact?
Well, that's the space of measures on space of probability measures on a compact space. Weak star topology. Okay, now we get to the exciting part, the metric. Okay, so this is number 4 here. I have 8 bits here. I might not get to the last one, or maybe even. Okay, number 4 is the Lipschitz metric. And the dictionary says that this is, this could be Teichmüller metric. It sort of has features of all 3 of these: the Weih-Peterson metric or the Thurston metric. We only have one. There's only one useful metric. Well, there's also, you can also symmetrize, as you'll see, but we don't have a large amount of choice here. Okay, so let's say I have 2 points in. So here's my CVN, and I take 2 points that. So there's G gamma and there's G prime gamma prime, and I want to determine the distance between them. So I look at my diagram. So there's Rn, there's G going to gamma, G prime. So first there's a homotopy class of maps that's determined by this picture. Namely, you put a map here, say F, so that this diagram commutes. If you can put an isometry, then the 2 points are the same. But you can always put a map. Okay? And this map is called the difference of markings. Difference of markings. And you try to minimize the Lipschitz constant, which you can do by Arzello-Ascoli. So you take the minimal possible Lipschitz constant, and you call that number, say, sigma. Okay, so, and then I will drop G and G prime from notation, so I'll just have sigma of gamma gamma prime is the minimum Lipschitz constant of F, where F is difference of markings. Difference of markings. Okay? And the distance is declared to be the log of this number. So the distance from gamma to gamma prime, by definition, is log of sigma. Okay? So for example, the distance from gamma to gamma is 0 because it's log of 1. Right? The minimal Lipschitz constant is going to be 1 for when gamma is equal to gamma prime. And maybe it's slightly trickier to prove that if the distance is 0, then the graphs are the same. Okay, so let's work out an example. So let's say I look at the following picture. I have here's a graph. I want the length of this loop to be 1/4, 1/4, 1/2. And then over here, I'll have maybe a different looking graph like this, where all edges have length 1/4. Okay? And I want the difference of markings F to send this vertex to, let's say, a point in the middle here. So I'm just giving you a map. And then it's supposed to be obvious what to do with the rest. So if I take a loop like this, here's the left loop. Well, that should go to the left loop. So I'm just going like this way, and then go around here, and then come back. Okay? And likewise, the right loop will go over here, and then this top loop will go to the middle loop. Okay, so there's sort of an obvious map. That's what I want. Now, if you think about what the slopes are, you'll see that the slope on each edge. If you imagine that the map is sort of linear, with constant slope on every edge, then the slope is equal to 2 on these two, and it's equal to 1 on the top loop. Okay. So so certainly sigma is less than or equal to 2. But I want to convince you that you cannot do better, that 2 is really the best you can do here. And the reason for this is that we look at this graph where the slope is maximal, which is this graph here. And traditionally, this is called the green graph. And the organizer didn't supply green chalk. But it's OK. I don't see any green, but anyway. In the middle of the desk. Oh, this?
No, it's not.
No, that's white.
Terrible already.
It's OK. It's OK. We can call it a white graph just today. OK. Now, in addition, there's an extra structure that this graph comes with just by looking at this picture. So, and this is called a train track structure. So what is the train track structure? It is just an equivalence relation on the set of directions out of every vertex. Okay? So train track structure on a graph is an equivalence relation on the set of directions out of every vertex. And there's going to be a train track structure on this subgraph. So I'm going to call, so delta of F, this is the tension graph. Okay, so this is where the sort of maximal stretch happens. We call it the tension graph. And this graph comes with a train track structure. What is the train track structure? I need an equivalence relation on these 4 directions out of this vertex. Well, I'll declare that 2 of them are equivalent if F, or more precisely the derivative of F, think of these as kind of tangent vectors, are mapped to the same direction in the target. Okay, so 2 directions, D1 is equivalent to D2 if and only if, say, F star of D1 is equal to F star of D2. So here, in this picture, these two directions on the left are equivalent because they both go to the direction here, and the other two are also equivalent to each other because they go there. So traditionally, we're supposed to draw this picture like so. So this is in the spirit of Thurston, you draw a tension graph like that, where you draw equivalent directions in sort of tangent way. And there's a notion of a legal loop. A loop is legal, or a path. A path in delta of f is legal if at every vertex. Oh, I didn't. So an equivalence class is called a gate. So a gate is an equivalence class. Okay, so if at every vertex the enter gate is different from the exit gate. Right, so any kind of a smooth path here is legal. You're not allowed to come in and then turn around, make a sharp turn and go back. That would not be legal. And notice that if you take any legal loop, its length in the target is exactly 2 times the length in the source. All these edges get stretched by a factor of 2, and the loop remains immersed when you map it to the other side by the legality condition. And that means that you cannot do better. If there's a loop that stretches by a factor of 2, then there's no way you're going to have a Lipschitz map with Lipschitz constant less than 2 from one graph to the other. So this train track structure on this subgraph is kind of a witness to the fact that you cannot do better. So this is kind of like the quadratic differential in Teichmüller's theorem. And in fact, that's let me state the theorem, which is really analogous to Teichmüller's theorem. So the theorem is, so this is the dictionary is that this is the Teichmüller theorem. Okay, so for every gamma prime CVN, there is a difference of markings map say f from gamma to gamma prime called an optimal map and the dictionary is that this is the Teichmüller map. Unfortunately, it's not unique. There's some floppiness here. But the properties are, so one is that f minimizes the Lipschitz constant lambda, which is sigma of gamma prime. F has slope lambda on a subgraph. On the subgraph delta of F, this is the tension graph. If you're thinking analogy with the Thurston metric, then this would be there's a measured lamination that is morally equivalent to this tension subgraph that sort of testifies that you cannot do better in the Thurston metric. And F induces a train track structure on delta of F with at least 2 gates at every vertex. It would not be very interesting to have a train track structure with only 1 gate, because then you would enter that vertex and you would be stuck. You would not be able to exit. Okay, so that's the Teichmüller theorem. Okay, now the metric is not symmetric, and there are easy examples. just about, I mean, just pick any two random points, it's probably not symmetric. But symmetric. So for example, if I take this and I take like that, so this is maybe a half and half, and this is 1 minus epsilon epsilon. Then going from here to here, and the map is just a homeomorphism if you want. The left loop goes to the left loop and so on. So here the stretch is 1 minus epsilon over 1/2. So it's 2 times 1 minus epsilon, then you have to take the log of that. Right? That's the distance going from here to here. If you go the other way, then this epsilon loop has to stretch all the way to 1/2. So that's a log of 1 over 2, what is it? 1 over 2 epsilon. So that goes to infinity, you see. This distance is bounded by log 2, no matter how small you make the epsilon, and this goes to infinity. So, so it's cheap to go to infinity in outer space. You know, when epsilon converges to 0, you're converging to one of the missing vertices. So you're really going to infinity in outer space. But it's expensive to come back. So you should be careful when somebody offers you a cheap ride into outer space. You always ask for the price of the return trip. And this is somehow a new phenomenon. I mean, for these three metrics, this, you know, well, you know what happens here. But two of these are symmetric, and the terrestrial metric is not symmetric, but it is still it's not finite distance to infinity. In fact, when you have a metric space that's not where the metric is not symmetric, then there are two kinds of Cauchy sequences you can consider. If you have a sequence of points, you know, in the Cauchy condition, you can always measure the distance from a point to a point in the, you know, to future points in the sequence, or you can measure distances the other way around, from a more advanced point to a less advanced point. So there's kind of a forward completion and a backward completion. So it turns out that this space is not forward complete. Well, this example shows you that. And the completion was worked out by Algom-Kfir. And it's remarkably similar to the Wei-Peterson completion of Teichmüller space. There are strata and so forth. And but it is backward. It is backward complete. So you can have it both ways. You know, whichever you like better, you can have that. Complete or not. So this somehow, you know, in some sense, replaces the fact that we don't have three metrics. There's just one metric, but you can think, you know, there's a forward direction and backward direction. It gives you a choice. Okay. Folding paths. So the dictionary is that these are Teichmüller geodesics. So these are going to be geodesics in the Lipschitz metric, but there are other geodesics. These are not the only geodesics. There are many geodesics, but these are somehow preferred. Those behave particularly nicely. So how are they defined? Well, I'll be only loose here. So if you have an optimal map, like in the theorem, this is optimal, and the tension graph is the whole thing. Okay, so that example is not good because we don't know what to do with edges outside the tension graph. We want the tension graph to be the whole thing, and then we say, well, fold all illegal turns at the same speed. Okay, then fold all illegal turns of this, you know. So now we have a train track structure on the whole graph gamma. Fold all illegal turns with the same speed, and this is going to produce a path, say gamma sub t, from gamma to gamma prime. I mean, just to give you a local picture, it's something like, you know, maybe this is your train track map with the, you know, there are 3 gates at this vertex, these two edges are in the same gate. There's an illegal turn there. So you can just, in this picture, there's only one illegal turn. So the same speed, I mean, there's only one. Then you just OK, so what you do is you take a piece of this edge of length t and a piece of this edge of length t, and you identify them. So maybe the optimal map went to something like this. Yeah, I'm really cheating because this is not, it's not too exciting like that. But anyway, just take a piece at time t. You take a piece of length t, a piece of length t, and you identify. So this is going to factor through a graph like that. Okay, and then you get a factorization like this. If you do this for all possible t's, you'll get a path. This is, of course, more interesting when the map is complicated. Maybe you have something like, an automorphism where A goes to AB, B goes to BAB. This is in kind of a self-map of a graph. And then it turns out that if you maybe take a high power of this map with appropriate metrics, and then this folding path will just take the bigger loop and it'll fold it over the smaller loop, and maybe as a result the bigger loop will become smaller. So it's kind of like a continuous fraction expansion or something. You're folding a bigger loop over a smaller loop until it gets smaller, then the other loop, and then you do it the other way around and so on. Okay, so that's what a typical folding path looks like. All right. Okay, so number 6. This is probably going to be the last one. I don't think I'll get to 7 and 8. But number 6 is, so there's a classification of automorphisms. And this is directly analogous to the work of Bers. So Bers reproved the Nielsen-Thurston classification of automorphisms from the point of view of Teichmüller theory. And you can do exactly the same thing in outer space using the Lipschitz metric. So the idea is that if you, suppose I give you an automorphism in out Fn, well, this is going to act by an isometry on outer space. So this induces an isometry, CBN to CBN, and then you have the displacement function. B sub phi, and this is just some function defined on CBN. It goes to 0 infinity. In sense, you take a point in CBN, which is a graph, and you look at its image. Okay, so and you measure the distance between the point and its image. And I like to write the action on the right. You sort of have to be careful how the order is important here. But this is the right one. And then there is just a logical trichotomy, right? You can say that phi is can be elliptic. It can be hyperbolic, or it can be parabolic. Okay, so the elliptic means that the infimum of d phi is 0 and is realized. In other words, there is a point that's fixed by this isometry. That's the same thing as being elliptic. Hyperbolic means that infimum of this function is positive and is realized. And parabolic just means that infimum is not realized. It could be 0 or positive, but it's not realized. Okay? And in the surface situation, elliptic corresponds to finite order, hyperbolic corresponds to pseudo-Nassau, and parabolic corresponds to reducible. In outer space, it's a little bit more complicated. Namely, The first part is still okay. So the elliptic still corresponds to finite order. And that's almost obvious. I mean, the elliptic means that there is a point fixed by this isometry. And if you examine definitions, that means that the automorphism can be realized as a symmetry of the underlying graph. So it's finite order. Finite order. Now, the other two are not going to be if and only if statements. I mean, in fact, it's still not completely understood which elements are hyperbolic. But okay, but parabolic certainly implies a reducible. Okay, and I didn't tell you what reducible means, but here's an example. If I take, say, A goes to A, B goes to AB. So here's an automorphism. This one is reducible because it has this, it's realized on a graph with an invariant subgraph. I have this loop A that I'm going to draw very small, and then the loop B that I'll draw big. So the loop A has length epsilon, and B has length 1 minus epsilon. If you think about what this map does here, its Lipschitz constant is going to be very close to 1, just slightly over 1. So so that means that the displacement function on this graph is very close to 0. But it can never be 0 because this automorphism has infinite order. So that shows that this is parabolic. The infimum is 0, but it's not realized. Okay, so that's parabolic. So parabolic always implies reducible. But there are reducible automorphisms that are not parabolic. But I won't get into that. And then finally, the most interesting thing, so fully reducible is what corresponds to being pseudo-Nassov. This always implies hyperbolic. Hyperbolic, and it translates and has an invariant folding path along which it translates. So that's kind of like an axis along which it translates. And the translation length is log of the dilatation, just like in the case of Teichmüller. So what does fully reducible mean? Well, it means that it does not preserve the conjugacy class of any free factor even after taking powers. So there's no periodic, there's no free factor which returns to itself, maybe conjugate of itself, after taking powers. This is so here a free factor is analogous to being a subsurface, right? So you can define a pseudo-Nassov as saying that it's something where there's no subsurface that returns to itself after taking powers. But here, instead of saying subsurface, you say a free factor, and you get a definition of a fully reducible. And all those guys are hyperbolic. They translate along some axis, which is really a folding path, which is like a Teichmüller geodesic. And it has the right translation length. The translation length is log of the dilatation, which is the growth rate of the automorphism. And this actually shows why a metric like this has to be non-symmetric, because it turns out that there are automorphisms. In fact, a typical automorphism is going to have different growth rate than its inverse. So the automorphism grows at one growth rate, the inverse grows at a different one. So if you want the statement about having translation length equal to the log of the growth, then you're forced to look at non-symmetric metrics. Okay. All right. So maybe I'll say a few words about the more recent developments. This is about complexes. So these are analogs of the curve complex. So here we had only one metric, while the Teichmüller theory has three metrics. With the complexes, the situation is reversed. We have at least three complexes that play the role of a curve complex. So 7 complexes. And the dictionary says curve complex. Yeah, so there are three of them that were at least three, actually. There are more, but for this talk, there are three. There is FSN. So this is the complex. So this is the free splitting complex. And a typical vertex in this complex is represented by a free product, which I'm going. So Fn, A star B like this, and I like to think of it as in terms of the Passer correspondence. I want to draw a picture like this, where this is 1. Okay, so this is a free splitting of the free group. That's a typical vertex. You can imagine, so there are some elementary moves that tell you how to fill in the complex. For example, you can split B as a free product, B1 star B2, and then you can put B1 on the A side. Okay, so that's an edge in this complex. But let me not talk about that too much. The time is running out. Okay, and then there's the free factor complex. See, in the surface world, if I give you a subsurface, then there's a unique complementary surface. In the free group setting, if I give you A, right, there are many different B's you can put here. Essentially different B's. And so in this complex, we don't remember the B, we just remember the A. Okay, so this is the complex. So this is kind of like the Brouhat-Hitz building. But instead of subspaces of a vector space, you consider three factors, and simplices are just going to be things, flags. They're induced by inclusions. And then there's also an intermediate complex, which is FZN, which is the cyclic splitting complex, where basically you take splittings over a cyclic group. Instead of a trivial group, you get to put a Z here. And they're coarse maps. So CVN coarsely maps to this complex, this coarsely maps down here, this coarsely maps down here. For example, what is the map that goes from, well, let's forget the cyclic splittings. Let's just think about going from here to here. Well, you just pick, say, A, right? Or you could pick B, but it turns out they're close in the free factor complex, so it's a well-defined coarse map. These are all like invariant coarse maps. And they're not quasi-isometries. They're all these complexes are really different. And the theorem, due to maybe too many people to list at this late hour, is that all three are hyperbolic. All three complexes are hyperbolic. And okay, yeah, I mean, I guess it'll go on and on, but so I think you see that there is kind of a reasonable theory that tries to mimic what's known for in the Teichmüller theory case, but there are also many differences, and there are also many things we would like to know, but we don't. For example, the one that's bothering most of us is the lack of the distance formula, the Maser-Minsky distance formula, where you can estimate the word length in OutFN in terms of some data that come from these complexes. So we don't have that, and I guess we're trying to work hard. And I think I'll stop here.